LRK parsers are like detectives that read a sentence from left to right, the L in LR, and use a small amount of future information up to K symbols ahead to decide what to do. The K stands for look ahead. Imagine you are walking down a hallway and you can peek a few steps ahead to see which door you should take. Formally, a grammar G equals NTP. S consists of non-terminals N, terminals T, productions P, and a start symbol S. LR0 needs no look ahead. It decides solely on the current state. SLR1 and LALR1 need exactly one token of look ahead, but use different ways to compute it. CLR, canonical LR1, also uses one token, but with the most precise computation possible. The hierarchy of power is LR0 is a subset of SLR1 is a subset of LALR1 is a subset of CLR, LR1. Any grammar that can be parsed by a weaker method can also be parsed by a stronger one, but not vice versa. Think of an LR0 item as a snapshot of a production with a dot, showing how much of the right-hand side we have already seen. For example, the production A goes to BC becomes 3 LR0 items. A goes to .BC, A goes to B.C, and a goes to BC. To build the LR0 automaton, start with the augmented grammar, add a new start production S' goes to S compute the closure of the initial item set. Repeatedly add items whose dot is before a non-terminal, inserting all productions of that non-terminal with a dot at the beginning. This is like expanding a family tree until no new members appear. Next, for each symbol X, terminal or non-terminal, define a go-to operation that moves the dot past X in every item where X follows the dot, then take the closure of the resulting set. The collection of all distinct closure sets reachable by go-to forms the canonical collection of items, which are the states of the LR0 automaton. Each state tells the parser what could we have seen so far. An SLR1 table is built from the LR0 automaton, but adds a simple look-ahead rule using follow sets. The follow of a set contains all terminals that may appear immediately after a non-terminal A in some valid sentence. Imagine you have a list of friends who might call you after a meeting. Follow tells you who could appear next. When a state contains an item of the form A goes to alpha dot, it means we could reduce by the production A goes to alpha. In SLR1, we place a reduce action for every terminal in follow of A. If two actions clash, for example a shift and a reduce for the same terminal, we have a conflict. Because follow is a coarse approximation, some grammars cause conflicts even though they are actually deterministic. SLR resolves them only if the conflict does not appear in the follow set. The table has two parts. Action of state and terminal equals shift S sub j, reduce R sub I except or error. Goto of state and non-terminal equals state number to go after a reduction. The parser uses this table to decide at each step whether to read a new token, a shift, or replace a sequence of symbols by a non-terminal, a reduce. Canonical LR1, often called CLR, uses exact look-ahead for each item instead of the coarse follow set. An LR1 item is a pair A goes to alpha dot beta, where A is a specific look-ahead terminal that may follow the production in the source program. The closure operation now adds items with look-ahead computed by the first function. First of beta, A equals case first of beta if epsilon not in first of beta. Otherwise first of beta without epsilon union first of it. When we move the dot over a symbol X, the new look-ahead for the resulting items is exactly the set of terminals that could appear after X in the original context. This precision eliminates many conflicts that SLR cannot resolve. The construction steps. Step 1. Start with the augmented item S' goes to $S$, where $$ is end of input. Step 2. Compute closure using the LR1 rule above. Step 3. Define goto for a symbol X by shifting the dot and keeping the appropriate look-ahead sets, then take closure again. Step 4. Collect all distinct item sets. These become the states of the CLR parser. Because each state carries specific look-ahead tokens, the action table entries are unambiguous for any deterministic grammar, giving CLR the full power of LR1. The trade-off is that the number of states can be very large, often exponential, because each different look-ahead creates a separate item. LALR1 stands for look-ahead LR1 and tries to get the best of both worlds. the power of CLR with a table size close to SLR. The idea is to merge states that have the same LR0 core, the same items without look-ahead, but possibly different look-ahead sets.
Well, steps.
1. Build the full CLR collection of LR1 items. 2. Group together all states whose LR0 cores are identical. Think of it like stacking several similar puzzle pieces on top of each other. 3. For each group, union all look-ahead symbols from the merged states. The resulting combined state now has a single set of items with a merged look-ahead. 4. Recompute the action and go-to entries using the merged look-ahead sets. The result is usually a much smaller parsing table, often similar in size to an SLR table, while still resolving many of the conflicts that SLR cannot. However, because we lose some look-ahead precision during merging, a few grammars that are CLR compatible become ambiguous for LALR. Such grammars are called LALR conflicts. Parsing power: what class of grammars each can handle without conflicts. LR0 is the weakest. It cannot handle any shift/reduce conflict. SLR1 handles more grammars but still fails when follow sets are too coarse. LALR1 is almost as powerful as CLR, covering most programming language grammars used in practice. CLR, canonical LR1, is the strongest. Any deterministic context-free grammar that can be parsed by a bottom-up method is LR1. Table size: number of states times number of terminals and non-terminals. LR0 and SLR1 tables are usually small, tens of states. CLR tables can blow up to hundreds or thousands of states, because each distinct look-ahead creates a new state. LALR1 tables are close to SLR size because merging collapses many CLR states. Runtime overhead: time per parsing step. All three use the same basic algorithm. Look at the top of the stack, consult action, push, or pop. The difference is in table lookup cost. Larger tables may cause more cache misses. In practice, LALR parsers, for example Yak and Bison, run almost as fast as SLR while offering CLR level coverage, making them the sweet spot for most compilers. A quick visual analogy: imagine you have a library, the parsing table. LR0 is a tiny bookshelf with few book states. CLR is a massive warehouse with a separate shelf for every possible book and version. LALR reorganizes the warehouse, stacking books of the same title together, saving space while keeping most of the content. Explanation: choosing a parser generator is like picking a tool for a job. Use SLR if the grammar is tiny, well-behaved, and you want the simplest table with the least memory footprint. It is rarely chosen for real programming languages because most languages need more look-ahead. Use LALR for most production compilers. It gives you the parsing power needed for C, Java, Python-like languages, and the tables stay compact. Tools like Yak, Bison, and many IDE parsers default to LALR. Use CLR only when the grammar is exceptionally tricky, and LALR still reports conflicts after attempts to refactor. Some domain-specific languages or academic experiments opt for CLR to guarantee correctness. Practical checklist: 1. Write the grammars. 2. Run an SLR generator. If no conflicts, go with SLR. 3. If conflicts, try LALR. If none, choose LALR. 4. If LALR still conflicts, either refactor the grammar, see next topic, or switch to CLR. 5. Consider memory limits of the target platform. Embedded systems may still need SLR. Remember, a larger table does not automatically mean slower parsing. Modern CPUs handle thousands of table entries easily. The biggest concern is maintainability. Simpler tables are easier to debug. When a grammar produces conflicts, we can often rewrite it without changing the language it accepts. Some common strategies. 1. Left factor: pull out common prefixes. Example: original, a goes to a B or a C left factored. A goes to a X, X goes to B or C. This removes a shift/reduce conflict because the parser no longer has to choose between two productions after seeing the same prefix. 2. Eliminate ambiguous recursion. Replace left recursion with right recursion for LR parsers that cannot handle left recursive look-ahead properly. For example, E goes to E plus T, or T becomes E goes to T E prime goes to plus T E prime or epsilon. 3. Introduce explicit precedence and associativity declarations, often supported by parser generators. This tells the parser to prefer shift over reduce, or vice versa, for operators like plus and asterisk. 4. Split productions. Break a production that mixes operators of different precedence into separate non-terminals, mirroring the natural hierarchy of expressions. 5. Add dummy non-terminals for optional parts to keep look-ahead sets tight. For instance, instead of STMT goes to if expr then STMT else STMT and STMT goes to if expr then STMT, create if STMT goes to if expr then STMT opt else where opt else goes to else STMT or epsilon. Applying these refactorings often turns an SLR conflicting grammar into an LALR friendly one, and in many cases even an LR0 grammar. The key is to keep the parser's decision points simple. At any moment, the next token should give a clear hint about which rule to apply. The parsing algorithm works with two main data structures. Stack holds a sequence of state numbers and grammar symbols. It starts with a special bottom of stack marker 0. Input buffer the stream of tokens, followed by an end of input marker $sign. The loop repeats. Look at the state on top of the stack, call it S, and the next input token A. Consult the action table entry action, left bracket S, a right bracket. If it is shift S prime, push the token A and the new state S prime onto the stack and advance the input pointer. If it is reduced by a produces beta, pop 2 times absolute value beta item symbol state pairs from the stack. Look at the new top state T, push the non-terminal A, then push go to left bracket T, a right bracket the next state. If it is accept, the parse succeeds. If it is error, report a syntax error. A visual analogy: imagine the stack as a train of cars, states, and passenger symbols. A shift adds a new car with a passenger at the front. A reduce removes a few cars that form a known train segment beta and replaces them with a single deluxe car A that represents the whole segment. The go-to table is only consulted after a reduction to know which state to move into after we have recognized a non-terminal. All operations are O1 table lookups, making the parser run in linear time with respect to the length of the input. Explanation: let us parse the tiny arithmetic grammar : E goes to E plus T or T new line, T goes to T times F or F new line, F goes to left parenthesis E right parenthesis or id. We will walk through the 3 parser types period. Step 1: augment and compute items omitted for brevity. The LR0 automaton gives us states I0 through I7. SLR1 table dash using follow sets : follow of E equals $sign and right parenthesis. New line, follow of T equals $sign right parenthesis and plus. New line, follow of F equals $sign right parenthesis plus an asterisk. The action entries place reductions for each production in the columns of these follow terminals. Conflicts appear for the left recursive productions shift/reduce on plus and asterisk. The SLR table reports a conflict, so plain SLR cannot parse this grammar. LALR1 table dash after building the full CLR states, we merge the states with identical LR0 cores. The merged look-ahead sets resolve the previous conflicts because the precise look-ahead from the CLR items tells the parser that after seeing plus, the only viable action is to shift, not reduce. The resulting LALR table has no conflicts and is roughly the size of the SLR table, about 12 states. CLR table dash each state retains its own look-ahead. The action table is larger, around 20 states, but every entry is unambiguous. For example, in the state that has the item open parenthesis E goes to E dot plus T, close parenthesis, the look-ahead can be any of $sign right parenthesis plus asterisk. The table tells the parser to shift on plus and to reduce on other terminals. Parsing an input id plus id times id : Step 1: initialize stack open bracket 0 close bracket, input id plus id times id $sign. Step 2: shift id leads to stack open bracket 0, id, 5 close bracket. State 5 after shifting id. Step 3: reduce F goes to id, pop id in state, push F, go to state 4, resulting in stack open bracket 0, F, 4 close bracket. Step 4: reduce T goes to F, resulting in stack open bracket 0, T, 3 close bracket. Step 5: reduce E goes to T, resulting in stack open bracket 0, E, 2 close bracket. Step 6, Shift plus, resulting in stack open bracket 0, e, 2, plus, 6 close bracket. Step 7, continue similarly, Shift id, reduce to F, then reduce to T, then encounter asterisk which causes a shift because of precedence, and finally reduce the whole expression to E. Both LALR and CLR produce the same successful parse. SLR would get stuck at step 6 because it cannot decide whether to shift plus or reduce E goes to T. This example shows how LALR keeps the table small while still handling the typical expression grammar that SLR cannot.